Okay, so before the break we got through almost everything that I wanted to say about how we impose strong boundary conditions, or how we can, and in particular how Firedrake does. Before we move on to look at vector function spaces, I just wanted to make a couple of points about how the implementation of this then works, because you've probably got some code somewhere which knows how to assemble this guy. And in Firedrake and Phoenix land, that's automatically generated, but it can actually just be handwritten code which does this problem. And so what you then want to do is to produce this system using the code that does that. And if you code your finite element method in a rather conventional way, which is to say that you have a kernel function, and that kernel function assembles the local element tensor. So what does that mean? It means that we visit one element, and if we were in P1 again, just to keep my life simple, I assemble the 3x3 local element contribution, which is caused by integrating j for phi I and phi j for each of the 3 phi i's and j's that are in here. That's what gets you a little 3x3 system. And then what you do is you go and add each of those values to the corresponding global matrix value by looking up which degrees of freedom these actually were. That's the standard way of doing the global assembly operation. We talked about it a few weeks ago in this course. And so what goes wrong now? Well, what goes wrong now is that one or more of these degrees of freedom might be a boundary condition. So this one here, for example, might be a boundary condition, or more of them, but let's just stick with one for the moment. So what I really wanted to assemble here was not actually this thing. I wanted to assemble this bit, and 0, 0, 0, 0, and I can put a 1 in there. Turns out that you can put a 1 in for every element and it will cancel as long as you do that on both sides. Or I could not put a 1 in there and put the 1 in later. But that's what I really wanted to do. And you can modify your code for doing this kernel operation to check every time if this is a boundary condition and do the right thing and only put the 1s and 0s in. If you had, very tight specialized code at this level with no branches and stuff in it, you may well have just done something horrible to your performance. And it certainly means you have to pass down the information about which of these are boundary conditions down into the kernel. That's all a bit messy. So it turns out there's a much neater way of doing this. What you do is you assemble this whole thing, assuming that that wasn't a boundary condition node. And now when you write stuff out into the global matrix, you chuck out that information. And if you happen to be using PETSI, there is a convenient way of chucking it out. And the convenient way of chucking it out is what you do is when you set up your global indirection maps that says that this triangle is composed of values, 24, 72, and 137, you lie a bit. And for the Dirichlet conditions, you set that to a negative value. Set to a value which is outside the bounds of your matrix, which in particular a negative value is. And what happens when you do the PETSI global insertion and you say insert this into, well, in this case, row minus 42, column 27, it just goes, oh, minus, don't know how to deal with that, drops it on the floor. Goes away. Simple, efficient, life's great. And so that's how it's done. And if you do it that way, you almost get the right answer. The only thing you get wrong is you don't get the ones on the diagonal. But in most matrix formats, addressing the diagonal is a simple thing to do. And so you can just go back, loop over the boundary condition nodes, which I remember are, in general, a small and vanishing proportion of your nodes, and set the ones back in. So that gives you a very simple, convenient way of imposing this system. And that's at least how Firedrake does it. I think in some circumstances it's how Dolphin does it. Dolphin has multiple ways of imposing strong boundary conditions, so that's a different story there. So that really is everything that I wanted to say about strong boundary conditions. So now we're going to go and talk a little bit about vector function spaces. So almost everything we've done so far, even when we've solved problems in more than one dimension, has been about fields which take scalar values. And that gets you quite a long way, and it's a standing joke, in fact, that many great careers in computational science have been built on solving Laplace's equation on the unit square. But if you wanted to actually do some real stuff, then there are many real applications where you really care about things whose value is a vector. And probably the most obvious example of this is if you're doing fluid flow, you have velocity. Right? So in the simplest versions of fluid flow, you have a velocity and something that looks like a pressure. So either actually pressure or surface height or something else that's a proxy for pressure. And so you need to be able to write down quantities which are vector valued. And there are a few ways of doing this, and they have different properties, and those are important. So there's a relatively simple one that we've encountered already, which we encountered it because it's how you write down the coordinate field. So a relatively simple one is to say, well, I can treat a velocity vector as a vector of scalar values. And I can then take each of those scalar values from any of the other finite element spaces that I could use for scalar values. And I can get a vector value function space like that. So how does that work? So that says, so I have now U, and for a little while at least I'll remember to write the lines under the U. It's not universally done in this field, right? Quite often people just write normal letters to mean vectors. In particular, the good Dr. Cotter feels that it's childish to write lines under your U's because you were just supposed to know. But for a little while, we'll keep those in there. And so U is some vector field, and so that means that I can write U as Ui phi I, and it's like that, right? Remember that in our function space view, our vector space view of how these functions work, the operations that are available are addition and multiplication by a scalar. So that means that a linear combination like this must be scalar factors times vector basis. Right, so I just have a big set of scalar values which multiply with the vector basis functions. So what do the vector basis functions look like? Well, if I was on a triangle, my favorite example, and I was in P1, then what I need, assuming that this is a triangle in 2 dimensions, right? So I can have a triangle immersed in 3 dimensions, and at that point I might want to have 3 components, but we'll just assume that this is a triangle and the triangle is in a 2-dimensional space. Then I'm going to have 2 components of velocity at each of these points. So that's 6 degrees of freedom and 6 basis functions. And I will try very briefly to sketch some of them. Sketching the vector value basis functions is a bit of fun, but we'll give it a go. And so there's a basis function which is for the x component of velocity at this point. And the basis function for the x component of this velocity at this point must take that value with, well, in any sort of sane conventional basis, length 1 at that point, and it must linearly decrease in length and never change in direction, so that it's a 0 vector here and a 0 vector here. And so if I was halfway along either of these lines, it would be a vector which was of length half, and it would get shorter as I went down this way, and it would get shorter as I went down this way. So it's longer up here, and it's 0 at any point along here. So that's the basis function. Of course, there was a much, much easier way of writing this. The much, much easier way of writing this was to realize that actually what I've just drawn is, let me go into a brief moment of Technicolor, is the scalar basis function, which is 1 here, goes down to 0 here, and goes down to 0 here. This thing times that vector. That's the construction of that basis function. And so now we can see what the local basis functions on one vector are going to be. So I try and be consistent with all the other notation, and for local basis functions I'll write big letters. So we kind of have the local basis functions, which just are 6 basis functions, but at this point it would be convenient to number them I alpha, and that is equal to phi I, where, whoa, hang on, can't do that. Okay, so this is the vector basis function. This was in a paper that I'd write this in bold. This is the vector basis function, I alpha, and that is equal to the scalar basis function I times, well, what do you want to call your Cartesian basis coordinates? Should we call them E? E alpha. And this is for I equals 1 to 3, or 0 to 2 if you count that way, and alpha equals 1 to 2. So those are 6 basis functions which are made out of the scalar basis functions multiplied by multiplied by the Cartesian basis for the Cartesian vector space. So what's going on is I've got effectively a tensor product element, right? It's a tensor product element where one of the spaces I had a basis for is R2, right? The normal conventional basis, and the other space I had a basis for is the scalar P1 space. So this one gets me my spatial variability, and this one gets me my direction variability. And so you can also, people then also write these out, and you can also, so you can say that you wrote this out like this, right? So these things are the basis functions. So the first one is going to be phi 1, 0, phi 2, 0, phi 3, 0, and then we're going to get another set of them which are 0, phi 1, and so on, 0, phi 2, 0, phi 3. That's another way of writing them in a sort of more graphical form. It's actually more helpful in many respects to write them down in an algebraic form like this. Because one of the things that this makes clear is what happens when I do this change of coordinates back to the local space. So I've written down the local ones here. The global ones are just the same, right? So the global ones, now it's harder for me to index them in 2 neat, well, I can index in 2 neat directions, but now this is that's a global index, J alpha, and the same thing is going to be true globally. So one of the things to notice about this is that the basis function, the spatial variability of the basis function, obviously transforms as we go from any real element out there back to our reference element. Right? We pull back along the transform. But the directional components of this do not change. Right? So when we're out on this element, these things are always in the x and y directions regardless of what direction this element's in. And when we come back here, they appear to be in 2 directions regardless of what's going on. So the transformation that applies to the basis functions due to changing this does not change the vectors. So that's really nifty, because it means that transformation, it's because the transformation is only a function of position, right? And so that transformation passes through this inner product. And so we don't need to do anything special. If we take a gradient in one of these fields, it's fine, right? We did the gradient before, so when we take gradients, so if we take when we took the scalar gradient, we had to remember that that was the little x gradient, which means that that is equal to the, that doesn't have an I. Right, that's how that varies. I'm trying to be consistent here and use Greek letters for spatial dimensions and Roman letters for the discretization dimensions. And so then we remember that that was equal to, I'll write it out. The x beta dx alpha phi right? So there's my Jacobian, inverse thereof actually in this case, inverse Jacobian, and there's my local gradient. So this is equal to inverse Jacobian times grad in big X of phi. And that's the one that I statically know, and that's my change of coordinates. This is what we've done 2 lectures ago or so. So what changes for these guys when when we go to, if we chose this to be vector valued? And the answer in this case is nothing. So I can take the, right, I can turn that now into a vector valued version just by writing that in, and nothing else changed. So I didn't need to make any transforms to do that. So life's really easy and life's great. So these things are straightforward. And this is why many finite element packages support these, because if you've got the scalar ones, then you basically just glue together some scalar fields and you get a vector ones. And those who work on fluidity, that's exactly what fluidity's got. Works straight out of the tin, no big surprises. Okay, so now we're going to do the other case. And the other case is harder. So the other case is the case where you didn't make your vector space by gluing together, but by taking a Cartesian product of scalar values, you directly chose vector valued degrees of freedom. Right, that's the other case that's going on here. And you guys actually know one of these, almost certainly. So if you've ever seen a finite volume method for a fluid, there's a really common discretization out there, which if you're a geophysical fluid dynamics person, you call the C-grid, and if you are almost any other sort of finite element person, you call marker and cell. Finite volume person, you call marker and cell. And in that setup, you have, maybe we'll draw quadrilateral cells for a while, it doesn't change anything at the moment. You have a pressure value in the middle of each cell, and in finite element land, we know how to interpret that. We say, well, that's equivalent to having the integral over the cell, so that's a P0, a discontinuous Galerkin piecewise constant degree of freedom. And then they do something else. Then they have one velocity component on each of these edges. That's actually the degree of freedom they're actually using there is the flux through the edge, the integrated flux through the edge, which you could point-wise interpret as saying that the velocity is the normal component of the velocity is constant along the face. It's another way of interpreting that same information. And so now somehow, whatever value this component of velocity takes here, it has to get to this value here. So it varies linearly across the element in that direction. And the x component of velocity varies linearly across the element in that direction. Right? And so the equivalent finite element, so if we take that off now and just worry about the velocity space, so that's the C-grid velocity, and the equivalent finite element space is called the lowest order Ravier-Thomas space. Now, there's a little issue down here. There is a disagreement amongst people in the field about how to number these things. So the original paper and most of the original work on this calls this the RT0 space. And the reason they call it the RT0 space is because not all of the linear functions are in this space. And that's trivially obvious, right? Because there are linear functions whose y component varies linearly across an edge. That's a linear function. So it's really obvious, and not all the linear functions are in that space. So the biggest space it actually spans is the constants. So that's why it's numbered 0. And if you do nothing else and don't have a particularly regular mesh or anything like that, then you do this and you get a first order scheme for that reason. However, you can also look at this the other way, and you can ask yourself, if I were going to use quadrature to integrate functions involving this, how much quadrature would I need? And the answer to that is, well, there are some linears in this space, so I need to take into account the linear functions in putting my quadrature in. And so the other way of numbering this is to say that this is RT1. If you hang around with a bunch of the people who we work with, because we used to say RT0 and then we encountered the Phoenix people who use the 1 convention, we have a tendency to call this counting in Norwegian. Because the core of Phoenix development for quite a while is being the Simula research laboratory in Oslo. So, but that's RT. So RT is now a challenging case because the important thing about these degrees of freedom is that the flux is constant. So that looks an awful lot like a reference element, right? That could be a unit square. If I'm out there in my horrible mesh and my element actually looks something like this, which is still a quadrilateral element, I need these things to look like this. Right? So that they're still the fluxes. We'll get on in a second to why they're the fluxes. And so when I do the transform, and I want to come back and do integrations on here, it's not the case that I can just take the vector values that I had here, or the vector component values, and use them up here, right? That's not true. So I have to transform back to this space somehow. I have to do a non-identity operation to transform back there. So what we're going to do in a minute is just start addressing what that transform looks like. I think we're not going to get through it all in this lecture, because I noticed that I probably only have about 15 minutes left. There's not enough time. But before we do that, I'd like to take a look at why on earth it is that we would choose to do something like this, given that we've got this other option, right? There are other function spaces out there which we get just by taking a Cartesian product of scalar function spaces and life spread them. And the answer is that we might want to be in a different sort of space. And for reasons that are kind of too deep to go into here, there are numerical reasons for wanting to be in particular places. I might sketch those. So let's remember the Sobolev spaces that we've encountered so far. So the places that we can take finite element function spaces from. And so one of them is L2. And now I'm writing the index down. That probably means that last time I wrote it up. Even I can't keep track of which way around we're writing L2 because everyone does it different. So L2 is a set of functions such that on whichever domain we're in, the L2 norm, which is the square root of u squared dx is finite. Right, that's the simplest case that we can have. So they are the simplest kind of well-behaved functions. And all of the finite element spaces that we are ever really interested in fall in L2. But we tend to typically talk about L2 when we're talking about the discontinuous spaces, because the discontinuous spaces don't fall in any tighter Sobolev space of interest. So in the L2 space, all we can say is that the L2 norm works out. And because all of the finite element stuff works using the L2 inner product, that's an important property, right? You needed that. Sometimes you needed more. So remember, we also then had H1, right, Hilbert space, and H1 is the space of functions such that, well, certainly in a circular sense, the H1 norm of them is defined and finite. But what was the H1 norm? Well, the H1 norm was equal to the integral of square root of the integral of u squared plus the square root of the integral of grad u dot grad u, or effectively the inner product's given by the weak derivative. So if your weak derivative is square integrable as well, then we're fine. And we had a whole lecture on basically these properties, and where we came to at the end of that was that because of the definition of the weak derivative, remember the weak derivative is defined in terms of a formula which looks like the integration by parts formula. So in order to have a weak derivative, then inside the domain, the surface terms from the integration by parts had to vanish. So what that meant was that to be in H1, you have to have continuity between the elements. And if we want to ask about H1 for vector functions, you need continuity in all the components, because you get a surface term in all the components in those cases. So, so our P1 space is in H1, and our P1 vector space that we just encountered is in H1. And in fact, P anything is in H1, and the non-equispace versions of P anything are in H1. And the serendipity elements that we looked at the end of the class a few weeks ago, so those are the ones where I take, for example, the quadrilateral P2 element, and I realize that that actually has too many nodes, and I would be including some cubic functions, and I'm not really interested in doing that. And so I can conveniently just get rid of the middle node. And so now I've still got a quadratic space, and I've got a quadratic space with less degrees of freedom and no interior degrees of freedom. There's a whole serendipity family based around those. And they're in H1, right? They have full continuity. That has quadratic continuity all around the edges. And if I made a vector version of that, that would be in H1. This guy's not in H1. Right? So this guy, this component here, that y component varies linearly up and down the element. And in the next element, the y component is also going to vary linearly, and it's only controlled by these flux values here. There's no continuity constraint there. So in these Rabiot-Thomas elements, the normal component is continuous because that's shared between the two sides. But the tangent component is discontinuous. And I can have the other sort of element as well. If I have an element whose degrees of freedom are effectively the vectors making up the circulation around the element, then I have the reverse case. When I glue two of these together, these share that degree of freedom, so the tangent component of their velocity is the same, it's continuous, and the normal component is going to be given by what's going on up here, and that will be discontinuous. So when we were scalar valued, we kind of only had two options, right? If you're scalar valued, you're either continuous or you're not at the edges. In almost all cases, you can be continuous at one point. That's a non-conforming element. That's a corner case. In the vector valued function spaces, we have way more options. And in particular, we can have continuous normal components, discontinuous tangents, or vice versa. And there's a particular reason why we might want to care about that. So the reason is, let's think about, and now I'm going to be stretching my drawing skills to the absolute limit. If I take a two elements and I ask myself, and I have linear functions on these, and they're continuous, so we're in H1, and I ask myself, so what are the, what's the best way to explain? Yeah. So what's the gradient of a function which is in this H1 space? And if I come to the edge of the elements, so the gradients, as we know of a linear element, have to be constant, but now we've got two components, so this is kind of tricky. And if I ask myself, what's the gradient in this direction? Well, there's a kink in the solution as I go over the edge, right? So in the direction normal to the edge, the gradient will be discontinuous as you go over the edge. But if you look at the gradient in the direction tangent to the edge, the slope on both sides of the kink must be the same in that direction. It smoothly goes through the slope of the actual line. So if I just pointwise take the gradient of an H1 function, I'm going to get a function which has discontinuous normals and continuous tangents. And I could also take the skew gradient, the perpendicular gradient, which is where I take the gradient and turn it through 90 degrees. That's important in rotating flows and things. And if I did that, I would get a discontinuous tangent and a continuous normal, because I've just rotated the vectors. So that's interesting, because typically our scalar and vector fields are related by derivatives. Right? So we might have that, I have a vorticity field, and the skew gradient of the vorticity field gives me the velocity, and then the divergence of the velocity gives me the pressure. That's a physical property. And it turns out to be very important to have finite element spaces whose numerical properties go along with the continuous properties that the original equations had. So that gives us a reason to want to care about these funny spaces which have partial continuity. And let's now think about what happens when we integrate by parts on a on one of these spaces. So let's think for a second about the case where I have the divergence of u. And the reason I might have the divergence of u, so where u is a vector field, is because I've got an incompressible flow. So I'm solving the equation, divergence of u equals 0. Now, what a weak form of the equation? So I have to ask myself, how do I make a weak form from this? So what sort of value is this thing? So use a scalar, sorry, use a vector, but div use a scalar. Right? So I'm going to be taking a value outside here, and so I can and so one of the things I can do is I can ask myself, okay, so when am I allowed to do this? When do I have a weak derivative that gives me a divergence? And to understand that, I have to understand what happens when I integrate this by parts. So if I integrate this by parts, this transforms into minus the integral of u dot grad p plus the surface integral of u dot n p dx. So this is exactly the sort of argument we were running when we slightly more formally argued about the need to have continuity when you want to take a weak gradient of something. So why did we have to do that? Because we needed the surface terms between the elements to cancel. So if I need my surface terms between the elements to cancel now, what I need is that this term is the same from both sides. Because then when I take the surface integrals around the two sides, I'll be going in opposite directions and they'll cancel. So what did I need? I needed that u dot n is continuous. Right? If u dot n is continuous, then this will be the same from both sides. I don't care what the tangent components of u are. Tangent components of u can be anything I like because they don't appear in this. So that enables us to define a couple of useful and interesting function spaces. So we can have h1 and we can have L2, which I've both now rather stupidly rubbed off. And we can now have the space H div on a particular domain. And this is the space for which the weak divergence, but not necessarily any other derivative, is defined. And it turns out that for finite element spaces, where we've got piecewise polynomials which are infinitely smooth inside the domains, and then we have something else going on at the edges, the continuity requirement for this one is that the normal component is continuous, and I can also have the H curl space. And so the H curl space is the space where I'm allowed to take the curl operator. So the curl operator in 3D is this one, and the curl operator in 2D is this. So it's just, you take the gradient and you rotate the resulting vectors by 90 degrees. So those are the curl operators. And in H curl, I can take a weak curl operator, but not necessarily a weak div or any other derivative operator. And for this case, because of Stokes' theorem, so this is basically because of Gauss's theorem that we ended up with a normal component, and because of Stokes' theorem you end up with a tangent component here. And so in this case it's necessary and sufficient in the finite element spaces that you have continuous tangent components. So in the two-dimensional case that's one tangent component, in the three-dimensional case it has to be both the tangent components have to be continuous. And so that's then where we get the spaces like the RT0 space or Collins' favourite space, right? So Collins' favourite space is the BDFM1 space. So we have normal components of velocity which are continuous between the elements and vary linearly along the edges, and a quadratic bubble which has 3 degrees of freedom, and that is constrained such that it has no components across the edges, so it's tangent to the edges, but it's discontinuous across them. So that's in HDiv as well. That's a much more complicated element, which is still in the HDiv space. And there are whole families of these, and in fact the Phoenix people are about to put out a beautiful poster which shows many of them. So we're going to leave that there now, because we're pretty much out of time. And so next time we're going to actually go back to the Rognitz 2009 paper and look at what you have to do to deal with the fact that as you move from a actual physical triangle back to the reference triangle, you have to turn around the velocity components so that they stay having this property of continuous normals or continuous tangents as you need it. That's it.